Hello everyone, my name is Hosun Jun at KAIST. Today I'm going to report the local magnification-induced interfacial artifacts at phase boundary in nickel-based superalloys. Let's start the presentation. This is the APTM map of TMS 1700 nickel-based superalloy after specific heat treatment. Mechanical strength and creep property of this alloy has changed after heat treatment, and this was analyzed with APT. The tip was aligned to the 100 direction of the lattice, and 2 gamma-gamma prime interface is shown in this atom map. In the proximity histogram of this atom map, 2 features are observed. First, unlike other elements, tungsten has a segregation peak at the interface, and second, the area and the height of this peak is different in different interfaces. In other APT data from same specimen, this difference in peak height was also observed. At the interface with gamma prime phase on the top, the peak was lower, and at the interface with the gamma phase on the top, the peak was higher. So we suspected that this peak height difference is more likely to be caused by an artifact in APT analysis and reconstruction. When we look at the voltage curve of this specimen, there is a voltage drop when the tip is analyzed from gamma prime phase into gamma phase. The voltage is increased again when the gamma prime phase appears again. This indicates that in our specimen, gamma prime phase has higher reference field than gamma phase. And when there is a reference field difference of phases, local magnification effects can take place. So, to confirm that the peak height difference is an artifact caused by local magnification effect, evaporation simulation was conducted using APTM software developed by Christian Oberdorfer. As a first step, virtual tip as an input data for the evaporation simulation was constructed with Python script. And second, field evaporation simulation with the synthesized virtual tip was conducted using APTM software developed by Christian Oberdorfer. And to investigate the effect of the local magnification effect, the evaporation field and the mass of each element were determined before evaporation. And as a result, detector XY position sequence for each simulation condition was obtained, and the resulting position data was reconstructed using standard shank angle reconstruction protocol, and reconstructed atom map was analyzed using IVAS 3.8 software. While TMS 1700 alloy has 6 elements as their component, we have simplified each phase as a binary solution of matrix element and solute tungsten. So gamma prime phase is consisting of 19.7% of nickel gamma prime and 3% of tungsten, and gamma phase is 19.7% nickel gamma and 3% tungsten in our tip. To study the effect of evaporation field difference, the evaporation field of nickel atoms in gamma phase were fixed as 35 volts per nanometers, and in gamma prime phase, it was varied about 35, 40, and 45 volts per nanometers. And tungsten atoms were set at 52 volts per nanometers. To observe was gamma prime to gamma interface or upper interface, and gamma to gamma prime interface or lower interface, the tip with 3-layer structure was made. These are the synthesized virtual tips before evaporation simulation. 2 types of tips, one with constant tungsten concentration of 3% all over the tip, and another one with 3% of additional tungsten segregation at the interface was made. The tip radius was 8 nanometers and shank angle was 10 degrees. The structure was FCC structure with lattice parameter of 3.6 angstroms, and the z-axis of the tip is aligned with the 100 direction of the lattice. And at the interface, proxygram shows that homogeneous 3% concentration of tungsten at the first tip and 6% of concentration layer with 1 nanometer width in the second tip. And the result of the evaporation and reconstruction is here. The simulation result of tips without interfacial segregation. From left to right, gamma prime phase had higher evaporation field. As it could be seen in the atom maps, the upper interface bends upward and lower interface bends downward as the evaporation field difference gets larger. And in the upper interface, no clear concentration artifacts were observed regardless of the evaporation field difference studied here. And in the lower interface, some sharp concentration fluctuation was observed when the different field was different, but in this result, no wide and high concentration peaks as in experimental data was observed. And these are the results from the tips with interfacial segregation. Similar to the previous result, the interface bends more when the different field difference gets larger. In the upper interface, interfacial tungsten concentration peak slightly gets lower and becomes narrower as the different field difference gets larger. And at the lower interface, the artifact is more dramatic, showing clear increase of peaks as the different field difference gets larger. These artifacts are related with the atomic density change at the interface. And here are some closed-up slides of interface in atom maps from previous slide. Blue and pink dots which represent the nickel atoms from gamma prime phase and gamma phase, and interface tungsten atoms are marked with red spheres. When we look at the upper interface first, tungsten atoms are compressed toward the interface as the field difference gets larger. This can be also seen in the density curve of the proxygram. The density of nickel is constant when the field of spheres were the same, but density peak at the interface shows up when the field difference gets larger because of the compression at the interface. And at the lower interface, we can see the detachment between phases, and the atomic density is low at the lower gamma prime phase. And this is also observed in the density curve here. At the detachment here, the atom density curve reaches its minima. And when we look a bit closer, there was an element dependency of this behavior. The minima of tungsten density curve, the red line here, is about 0.5 to 1 angstrom away from the minima of nickel density curve, the green line here. This is due to the relative position difference of nickel and tungsten from same atomic layer. When we plot a special distribution map of nickel and tungsten with tungsten at the center, we can see the average Z position of tungsten is 0.5 to 1 angstrom lower than that of nickel atoms. This is because tungsten is higher evaporation field than nickel. From the same atomic plane, nickel evaporates earlier than tungsten and reconstructs at the higher position in the reconstructed atomic plane. To find out the effect of the relative position of solute and matrix atoms, we have adjusted position of tungsten atoms in the reconstructed atom maps. With the same detector position data from the simulation, different atom maps with shifted Z position tungsten atoms were constructed. So the resulting atom maps have the same nickel atom positions, but with different tungsten atoms positions. And this is the special distribution map of nickel atoms calculated with tungsten atoms at the center. The green line is the special distribution map from the original atom map. And by shifting the position of tungsten atoms, the average Z position difference between nickel atoms and tungsten atoms from same atomic plane could be reduced or increased. With this atom map with different tungsten atom positions, the tungsten concentration profile from the proxygram of lower interface is given here. When the Z position difference of nickel and tungsten is small, the yellow curve in the STM and the yellow curve in the proxygram shows height of 6 atomic percent at the interface. But when the Z position difference gets larger, from yellow to blue curve, the peak height of tungsten concentration increases. When we look closer at the density profile and the concentration profile at the same time, we can see the cause of this artifact. On the left side, when the Z position difference is small, the minimum of density curve of nickel and tungsten is at the same position. And the concentration profile shows no height artifact here. But on the right side, when the Z position difference is increased, the minimum of nickel and tungsten density curve is separated. And at the minimum of nickel density curve, the total number of atoms within the beam is small. So when the tungsten concentration is calculated with small denominator, resulting in high concentration at the concentration curve. And at the minimum of tungsten density curve, the total number of atoms within the bin is large, so the denominator is large, resulting in low concentration here. This shows that combined effect of atomic density artifact and position difference of solute and matrix atoms could cause concentration artifact at the interface. To summarize, the effect of inversion field ratio between phases on the interfacial element concentration was studied using simulation. Concentration artifacts were more dominant at the lower interface in the gamma prime, gamma prime structure tip with interfacial segregation. When the tip is analyzed from low field phase to high field phase, S-shaped density profile across the interface is formed. And the density profile of each elements are at a different distance from the interface because of the different evaporation fields of solute and matrix atoms. Adjusting the position of solute atoms resulted in different concentration profiles, and this result indicates that the concentration artifact observed in the lower interface of the APT data is caused by combined effect of density artifact and solute matrix position difference. This is the end of my presentation, and thank you for listening.